In this problem, we're going to look at the transient response of an inductor. So let's say we have an inductor that is 20 millihenries, and we have an activation of a switch at t equals 0, and at that activation, then the voltage across that inductor is given as a function of time as 4e to the minus 0.2t millivolts for t greater than or equal to 0. And our job is to determine an expression I of t given that the energy stored in the inductor at t equals infinity is 0.64 millijoules. Okay, so for an inductor, the current at time t is given by its initial current, and I'm just going to call that I naught, plus 1 over L times the integral from t naught to t of v dt prime. And we use a prime here just to indicate that it's the variable for integration is different from this t that we're going to plug in, because this t that we're going to plug in is going to be the variable for our function, and we shouldn't use the same variable inside our integral as what we're going to plug in our limit of integration. So now, just plugging in the information that we have, I naught plus 1 over 20 millihenries is 0.02 henries, times the integral, and our starting time is 0, and we're going to put t up here because we want to get an expression for any time t of our voltage function, which is 4e to the minus 0.2t dt prime, 0.2t prime, dt prime, and that's in millivolts. And so when we do this integration, we get I naught plus 1 over 0.02 is 50. And then this integral, remember when you take the integral of an exponential function, that is just going to be that same exponential function. And if it's just a constant times the variable, then the constant, it's going to be, the integral is going to be this same exponential function divided by that constant. So divided by, that's supposed to be 0.2, not 0.02, divided by 0.2. And we're going to evaluate that from 0 to t, and since this is millivolts, this is going to be in milliamps. And so that equals I naught, and so this is plus 50 times 4 divided by 0.2 is negative 20. And then we'll get e to the negative 0.2t minus e to the 0. And it's important to remember that because we kind of think, oh, well, plugging in 0, that's going to be 0, but that's not the case when you have e, because e to the 0 is 1. and that's still milliamps. So now this is I naught, and 50 times negative 20 is negative 1,000. E to the negative 0.2t minus 1 milliamps. And then I'll go ahead and distribute this minus 1,000. So I get I naught minus 1,000 e to the negative 0.2t plus 1,000 milliamps. And so if I multiply through by this 1,000th here, then I can change I naught now. I can write it, well, if I hadn't put those parentheses in there, then the I naught does not have units yet. And so I can divide through by this 1,000 here with these that I have, and I have I naught minus e to the minus 0.2t plus 1, and now I can say these are all in amps. And so the I naught, I hadn't really said if it was milliamps or amps, but now it is amps. Okay, so notice, so one thing I should have pointed out at the beginning is we did not know what the initial current is. It did not tell us the initial current was 0. And so since they didn't tell us the initial current was 0, we couldn't assume it was, and that's why we had to carry it through all the way. Also notice, the I naught is not part of the integral, so you don't integrate that. Even if we had a number for it, you would not integrate it. So how are we going to use that? Well, we have some information about what happens at infinity. So let's find out what I of infinity is. So I of infinity is, and this is I for any time t. So we don't know what I naught is, but we do know that this expression works for I at any time t. So I at infinity is going to be the limit as t goes to infinity of I naught minus e to the minus 0.2t plus 1 amps. Now the limit of e to a negative exponent, the limit as t goes to infinity of e to a negative exponent, is going to be 0. Because this puts the e in the denominator, and if you have a number in the denominator that's getting bigger and bigger and bigger, when the denominator gets bigger and bigger and bigger, the value of the whole thing approaches 0. So the limit as t goes to infinity of this expression is I naught plus 1 amps. All right, so how does this help us? Well, we know at infinity the energy stored in this inductor was 0.64 millijoules. And we know that energy is given by 1/2 Li squared. And so the energy at infinity, which is 0.64 millijoules, is going to be 1/2 Li at infinity squared. So the energy was 0.64 millijoules, so that's 0.64 times 10 to the negative third equals 1/2, and L was 0.02. Let's see, what was L? L was 20 millihenries, so that's 0.02. So times 0.02 times our expression for I at infinity, which was I naught plus 1 squared. And now this is all in joules. Our expression for I was in amps, and we changed this energy. It was in millijoules, but we put the times 10 to the negative 3. So 0.64 times 10 to the negative 3 equals 0.01 times 0.02. So, sorry, the 0.02 is gone. So I did 1/2 times 0.02 is 0.01. I naught plus 1 squared. And now divide both sides by 0.01, and I get 0.064 equals I naught plus 1 squared. Don't know what's up with my pen. Very frustrating. So now we'll take the square root of both sides, and we get 0.2529 equals I naught plus 1. Now, when you take a square root, you theoretically get the positive and negative value. And when I did this, I couldn't see any reason off the top of my head why the negative value was not an option. So after I did this, I checked both of my answers. I did the positive and I did the negative, and then I checked them both to see if they both worked. And the positive square root worked, and the negative square root did not. So if we solve for I naught, then we get negative 0.747 amps. And so our expression for I of t, which originally we had as I naught minus e to the minus 0.2t plus 1. If we now plug in negative 0.747 minus e to the minus 0.2t plus 1, then we get our final expression of I of t equals doing a little rounding, 0.25 minus e to the minus 0.2t amps. These were amps. So what did I do to check to make sure that this gave me the right answer? You use this function here to find out what I at infinity is, and then you plug it in to the energy function, which is 1/2 L I squared, to see if you get the energy you're supposed to get. You're not going to get exactly the right answer because this was rounded some, but if you took the negative square root up here and you tried this, you would not get the right answer. So that's this problem, and looking at the transient response of an inductor. And again, what we're getting here is we're getting an expression for the current at any time t. So the voltage is changing at the switch activation. You're getting this voltage, and you get a current here for any time t, and you can see that eventually that the current becomes constant as t goes to infinity. which is not going to be the case always when you have a circuit that has more components in it.